Welcome back to this video series on AI in computer vision. In this video, we will learn how to build a CNN based classifier for a custom dataset using PyTorch deep learning framework. We will do it using what is called a transfer learning approach. For the purpose of this video, we will use a scene classification dataset, but you can use any of your custom dataset as well. This particular dataset consists of 6 classes, which are buildings, mountain, forest, glacier, sea, and streets. And what we want to do is to build a CNN classifier which can take any of these images as input and predict its correct class. To do that, we need to train this CNN with our custom dataset. But we need to know that a CNN contains millions of trainable parameters and we need millions of data to tune these weights. So obviously this is not possible using the limited custom dataset which consists of only thousands of images. So what we do is we use a pre-trained model which is trained with millions of images. This pre-trained model is capable of extracting several low-level features such as corners, edges, and also high-level features such as texture, shapes, and so on. And we will just fine-tune this model using our custom dataset. This is exactly what is called a transfer learning approach, where we transfer the previous knowledge and solve the current task and use it for the current task. So what are the things we need to do to build a CNN classifier for a custom dataset? So first thing is the data loading function, where we pre-process the data and make it in a format which can be taken as input by the CNN model. The next thing is we have to define the CNN model architecture, and for this transfer learning approach we need to initialize it with pre-trained weights. Next we define loss function and optimizer, and then we put all these things together and train the models. And once it is trained, we evaluate it on the test data. I would like to mention here that to train the model we need a GPU. So if you have a GPU, NVIDIA GPU on your laptop, you can train it on your laptop itself. But in case you don't have it, don't worry. In this video we will see how we can use an EC2 GPU instance of Amazon AWS, which is a cloud-based GPU service. So let's cover these topics one by one. So the very first thing we need to do is to download the dataset. For that you will have to go to this link and click on this download button. This will download a zip file as shown here, and I have already extracted it and placed in data folder. So let's see what this dataset consists of, the structure of the dataset. So it consists of 3 folders. This is for train and the test, and if you go into this, we have these 6 subfolders for each class, and each of this folder contains the required images. And whereas in the prediction folder we just have images, and we need to predict the class of each and every image in this prediction folder. So having understood this data, let's jump into the code now. So as I mentioned, the step 1 is a data loading function. So let's do that first. So to do that, we need to import the required imports, and in PyTorch we have this functionality. This is a subclass image folder, and we can just pass the path of the train set and to get the train data set, and we pass the path of the test set to get the test data set. So let's see what is this actually means. So let's run this. Well, this is a spider IDE, and I have chosen this spider IDE because we can run it line by line and see the output. So this is just for understanding purpose. And to run it, we have to click this button here, black button, and if we run this line, so what we have is train dataset. So it is a dataset consisting of 14,000 images, and the root location is this. So what? If we index this object, for example this, it will output the image and the corresponding label. If you just see, this is the image and the label is 0. So all the labels are encoded from 0 to n minus 1, where n is the number of classes. So this is the concept of this data set. So as long as we give the correct index, it will output the label, the image and the label. So this is the 100th image and this is the label. So we can use this as it is, but let's try to write this subclass by ourselves. So this will give us some more insights in what is going on, and we can even do something extra as per our needs. So let's try to do that. So what we do is we define the class subclass by name TL dataset. So this will have exactly the same functionality as image folder. So we are making the same thing but by ourselves. So we have to inherit this dataset class, and it consists of 3 methods which we need to code. So this dataset is an abstract class, and it consists of these 3 methods which are not implemented. So to write a dataset like this, we need to inherit this class and override these methods with as per our needs. So in this init method, we do all the initializations. So all these initialized variables will be accessible to that particular object instance, and this can be used by the remaining methods. So this is what init method does. And the len method, what we need to do is we need to write a statement which will output the length of the dataset. So whenever this method is called, we need to have the length of this dataset. And finally, in the get item, whenever we index the object of this class, as we had done here. So this is the object of this particular class, but when we create an object of our new class and when we index it like this, it needs to output the image and the corresponding label corresponding to that particular index. So this is the overview. So let's do it. So to do that, we need to have what is called a path file. So I have implemented it this way. So let's see what is this path file. So I have created train path file for train as well as test set. So let me show you this test path. So it consists of the label and the corresponding image path, and we have all the paths for all the images in the test set. Similarly, we do it for the train set. To generate this path file, I have written a Python script here, but you can use any of your methods. If you are good with shell scripting, you can do that, or you can even follow this Python code. I will share this code in the description. And once we have this path file, let's come back to this init method. So in this, if we want to do any transformations, we can pass it here while creating the object of this class, and these are saved in this init method. So transform is saved in self.transform, and the path file, regarding path file, we read all the lines and save it in self.paths. So this is basically a list of this entire path file. So the length of this list will be equal to the length of the lines, the number of lines in this path file. So obviously, to get the length of the dataset, we need to just return the length of this list self.paths. So this part is done. And whereas in the get item, we have to do this way. So we have to read the line corresponding to the index. So this is a list, and we extract the corresponding element of this list based on this index. And if you see, this line is separated by a comma. So what we do is we split it based on this comma, and that gives us the label and the image path. Please note that this is just a path and not an image. So we use OpenCV function to read the image, and by default OpenCV opens it in BGR format, and we need to convert it into RGB. So this is something a required step. And now we have a NumPy ND array image. So, and then if we if we have any transformations, we apply transformations to it, and we return the image and the label. So this is how we write our custom data set. So if we just run it, we can see that it has exactly the same functionality as this image folder, but with better control. So let's implement it, run this, and let's create the object of this class, new data set equal to the path is train paths.txt. So I have saved this path file in the same folder, so I'm just giving the name of the path file, which is trainpaths.txt. and let's do not use any transformations. So if we pass this transform equal to whatever transform we want, this will be applied in the getItem method. So for now, let's let's keep the transform as none for the purpose of illustration. So this is our data set, and as we have done earlier, if we index this data set, we will get the image and the label. So you see label, and this is now a NumPy array, so we may not plot it here. This image folder outputted a PIL image, so we could plot it. So here we can just see the shape of the image. So this is a color image with 150 cross 150 size, and we have not applied any transforms, so it is as it is by default. I mean the output of this OpenCV IMRead function. So now, having done this is a data set, but there is one important concept here. So now we have the data set, but ideally to train the model, we would like to give all the images to the model at once, but practically this is not possible. Why? Because if we are using CPU, it will require lot of CPU resources, and if we are using GPU, it will also require a lot of GPU memory, and this is not practically feasible. So what we do is we divide the data set into batches, and each batch is given to the model, and it is used to update the weights of the model. So this batching of the data set is created by DataLoader. So this is an important concept of dataset and DataLoader. So now, having understood this, let's do it for this case. So yes, so here I have created a dictionary containing the path file and the transforms. So for the train set, we use a certain set of transforms, and for test set we use another set of transforms. So let's see the transforms for train set. So here what we do is we resize the image to 250 cross 250, and these are basically the augmentations. Then we do random horizontal flips, so we randomly flip the image horizontally, and then we do random crops. And so this is actually the part of augmentation. This is necessary because every time the network sees the image differently, and that helps in the learning process. And finally, this is an important step. we need to normalize the images to have zero mean and unit variance. So for that we need to normalize it using this mean and standard deviation, so that it is in the range of 0 to 1. And so this is a dictionary for the train set, and similarly we have for the test set. In the test set we just resize it to 224 cross 224, and we do not apply any augmentations. So this is because every time we evaluate it we need to use the same image and we should get the same accuracy. So this is the thing. And then we create the object of train set and test set, and this is the subclass which we have just created. And we need remember that we need to give two things, the path file and the transforms. So we give it here. So what I have done here is basically train set configs is a dictionary, and when you do it this way it outputs the path file. So this is done this way. So we have train set and test set, and then we have data loader. So we need to create data loaders for train set as well as test set. In this data loader we have to pass the data set, the batch size. Let's keep it a higher let's keep a higher batch size. If you are training on GPU, we can increase this batch size depending on the GPU memory, and this batch size is basically the number of images in that particular batch. And we do shuffle equal to true specifically for train data loader. So what this means is every time we create the batches we shuffle the entire data set. So in each batch we get a different set of inputs. So this is kind of, you can say, another augmentation, and every time the model sees a different images in a batch, and also different augmentations in for each image. So this is the thing. Then we have the test data loader, and as you might have guessed, so we need to keep shuffle equal to false for the test data loader, and this is done. Okay, so let's implement let's run this up to this part. So before proceeding, let's see what is our data loader, means how it actually works. So data loader, we create a iterator of the data loader, and when we do a next of this iterator it gives us the images and the labels. And note that this is not just one image, it is the number of images is equal to the batch size of the initialized batch size. So if you see the length of labels, this will be 64. So every time you iterate this data loader it gives us a 64 batch size number of images and the corresponding labels, and this batch is then passed to the model for updates. So this completes the step 1, which is data loading. Then let's discuss the step 2, where we define the model and initialize it with pre-trained weights. So we import the required libraries, and for this particular case we use a ResNet model, ResNet 18 to be precise, and to load it with and to load a pre-trained model we say pre-train equal to true. So this is as simple as that. And so why we selected ResNet is because if you see the different model architectures, there are several architectures which are proposed, but this ResNet has a higher accuracy mainly because of a particular concept which is called skip connections or residual blocks. So this is something we will discuss some other time. So for this, let's just understand that this is a good model with high accuracy, as compared to other models, and also it has less number of parameters, or you can say the number of operations are less as compared to other models. So this is seen here, so that's why we have selected ResNet, and this is the ResNet model. Let's run it. So you can see this model by just typing here. So it consists of a sequence of convolutions and the activation functions. So this is a ResNet 18 architecture. So let's quickly go to the ResNet paper. The original ResNet paper is this, titled Deep Residual Learning for Image Recognition, and this is basically shows that even if you have deeper layers, and if you use this skip connection block or residual block, then you can make deeper layers, and those are trainable, and also it has higher accuracy. So for ResNet 18, this is the structure. So we are using ResNet 18 layer, a ResNet 18 model. So it consists of the first layer is 7x7 convolutions, and then it is followed by a ReLU activation and batch norm. So every convolution is followed by ReLU and batch norm, and then we have 3x3 max pooling, and then we have this set of blocks, and if you see there are total of 1 2 3 4 5 6 7 layers, but including the ReLU and batch norm, the total number of layers will vary. So finally we have uh, a fully connected layer, and the number of output neurons is equal to 1000. So initially this was used for ImageNet dataset, which consists of 1000 classes, and for our case what we do is we keep everything same up to the last layer, and in the last layer we just change the number of output neurons to be equal to the number of classes in our custom dataset. So what do I mean by that is, so in the last layer, if you see this fully connected layer, it consists of 1000 output neurons, and we just set it to 6 output neurons. 6 is because this is the number of classes in our dataset, and if we do this and print the model again, we see that the new number of output features or output neurons is 6, and this is all these layers are initialized with the pre-trained model. So our model is ready now, and we put the model on a GPU. So device is here. This is one line we need to run. So if you have a GPU on your laptop, it will set this device to CUDA, otherwise it will set to CPU. So accordingly we pass it to a GPU if you have a GPU, and then this part is done. Step 2 is completed. Next let's go to step 3, which is defining loss functions and optimizer and some other things. So let's import the required libraries. So since this is a classification task, what we use a cross entropy loss. So let's spend some time in understanding this cross entropy loss. So for example, the output of the model is these 6 values, which are called logits. So these values are in the range -infinity to infinity, and we apply softmax activation to it, and we get all the values in the range 0 to 1. And in the cross entropy loss, what we pass is this logits and the ground truth label. And for example, if the ground truth label is 1, we extract the corresponding value, which is b in this case. This is a number, any number from -infinity to infinity, and we map it to a value in the range 0 to 1. We interpret it as a probability which is predicted by the model. So what exactly do I mean by that is, the network predicts this class with this much probability, and we would like this probability to be equal to 1 ideally. And so once we apply softmax activation to it, it applies minus log of that probability. So this is what happens in cross entropy loss. So first we apply softmax to get a probability value or a value in the range 0 to 1 and apply minus log of that value. So if this p is equal to 1, or if the network predicts this p close to 1, we get a value which is close to 0. And if it is less than 1, then it gives a very high value. For example, if you see the plot of log x, so anything less than 1 you get very high value, and if it is, in the worst case, if it is 0, if the p is 0, then you get minus infinity, and minus infinity is positive infinity, so you get a very high loss. And this is how the network tries to minimize this loss. To summarize, what happens is, for a particular image we apply minus log of logits of label. This is the ground truth label, and if you see the documentation in the PyTorch, this is what happens. So x is the logit array, and you, for a particular class, we have the ground truth label, so we extract the corresponding logit value and apply softmax activation and apply minus log of that value. So if so you need to note that in this model here, the last layer is just the linear layer with no activations. So if you do apply activation such as softmax activation in the forward pass of the model, then you should not use this cross entropy loss, and you need to be careful in this. So if you do apply softmax activation in the last layer, then you need to use what is called negative log likelihood loss, which is NLL loss. So it just do this operation minus log of the value. So the softmax activation will give you this value, and you just apply NLL loss, which just do minus log of value. So this is one thing I wanted to mention. So this is the loss function. We are using cross entropy loss, as I have explained. And then we have optimizer. So there are various choices of optimizer. We use Adam here, and in this we need to specify which of the parameters of the model we want to optimize. So in this we specify that this con1 layer 1 to layer 4 we want to optimize. So which are, if you see the model definition, so this is layer 4, layer 3, this is the restaurant model, and in the last layer we have FC layer, fully connected layer. And we specify an important thing here. We want to have a higher learning rate for this last layer and relatively low learning rate for the remaining layers. So why we do this is because so what is learning rate? So learning rate controls how fast or slow the updates of weight happen. So since this is a pre-trained model, we want very minute changes in the upper part of the model, and we want high changes or high learning rate for this last layer. So that's why we set higher learning rate to the FC layer, and for the rest of the parameters we use a default learning rate, which is this. And then this is the optimizer, and then we also need to initialize a scheduler, define a scheduler, which is actually learning rate scheduler. So as the training progresses, we need to use a smaller learning rate because the model is learning as the training progresses, and we would like to have minute changes in the updates. So that's why we reduce the learning rate, and that is specified by the learning rate scheduler. There are various choices of learning rate schedulers. We have used step-LR. So this is basically after 10 epochs, after every 10 epochs, the learning rate will be reduced by a factor of 0.1. So this completes step 3. Now let's go to step 4, which puts all the things together, and this is basically the training loop. And I have created a separate file for the training loop, and I pass these parameters to this training function, which I have written in a separate train.py file. So the parameters are model, data loaders, loss function, optimizer, scheduler, and number of epochs. So this training loop is the same as we discussed in my previous video. So I'll just give a quick recap because we are already so it is already becoming a longer video. So I will quickly mention the important points. So we run the loop for the specified number of epochs, and in each epoch we run the training as well as testing loop. In the training loop we have to specify this model.train, and in the testing loop we need to specify model.eval. And so the thing what happens here is we iterate the data loader and get the images and the labels. So this is a batch, and the number of inputs is equal to the number of batch size specified in the data loader, and we put it to a GPU, and then zero out the optimizer gradients, pass the input to the model, and then apply call the loss function, which computes the loss using the outputs and the ground truth label as we have just discussed. And this loss in the training pass we back propagate it, and what happens here is it computes all the gradients of loss with respect to each and every weight, and optimizer.step does the main job of updating the weights based on these gradients, and this has to be done only in the training phase. And then we compute the statistics like epoch loss and accuracy for our visualizations. Then if it is a training step, you also need to call this scheduler.step. This is a learning rate scheduler, and these are just basic things like if the accuracy is better than the previous accuracy, we save a copy of the model just in case, so that you don't lose the model if the training loop is interrupted by any chance. So we have the best copy of the model, and so this is just to save the loss and accuracy for each epoch, and then finally we load the best model till now and return the model. So this is the training function, train model, and we call it here, and the output of this is a trained model which is obtained by training the model for 100 epochs, which we have specified here. So now this completes the entire pipeline. So if you have the GPU on your laptop, you can directly press the run button, but we will see next that how you can do it using a cloud GPU, which is in this case EC2 instance GPU instance of Amazon AWS. So I will make a separate video for this, and see you soon in the next video. Thank you very much.